over here is to have a noise controlled contrast and edge enhancement algorithm. Now, another problem is, say to some extent we can work upon enhancement of masses in these images, but again enhancement of calcifications is another problematic, because their visualization in a basic image is itself very difficult. So once it is not clearly visible or not clearly acquired in the input image, their overall enhancement becomes very, very difficult. So if we see this particular image, just by looking up to this image, it's very difficult to say that there is some calcification in these images. So this region of interest has been extracted out from this image. Say some enhancement algorithm is applied, but when this particular enhancement algorithm is applied over here, some visualization is there. You can make out that few calcium dots are visible, but again, not to a very good extent. Now say I have now tried to increase the intensity or to increase the parameters of my enhancement algorithm to get a more brighter image. But again, you see the unwanted noise is amplified. And because of this, most of the region has become unclear, although few dots are visible, but all the microcalcifications are again not very clearly visible. Now the last limitation, and a very interesting one, that is the image restoration challenge. Again, this restoration is not very clearly, evident in even most of the books. Say suppose we have our original image, a very common example image which we have seen in MATLAB and in our common books of image processing. So this is the image when, so this image has been encountered with some noise, and say this is your restored image. Now what happens if we want to improve the quality of this image? The basic procedure says I have to check this restored image with this original image, because I'm considering this original image as an ideal image. So I'll improve the quality of this restored image with the help of this reference original image. So every time I improve the quality, I compare it with this, and say at one extent or one point, I come to understand that yes, reasonable improvement of the quality has been ascertained. But this is not that simple, or you can say this is rather impossible. I mean, when you see medical image. Now, you see, this is the input mammogram, which is not clear because of the obvious reasons which I told to you. Now, it is in that form only. Now, this is, you say, is the enhanced one. Now, if I want to further work on further enhancement of quality of that image, where should I check it? If I suppose to check it with this image, this is not an ideal image because it is itself unclear. So the problem with this entire episode of medical image enhancement is that you don't have an ideal image with which you can ascertain the fidelity of your image. So that becomes the major challenge in, developing algorithms for enhancement. And even if you have developed the algorithm for enhancement, later on I'll tell you with few examples that assessing quality of these images is also a big challenge. So now, after we study these challenges in the medical images, we come to just an overview of these are the common approaches which could be deployed for mammogram enhancement. See, if you explore literature, advanced version of these techniques are available, but somehow the fundamental techniques always remain the same. And as regards my research on this arena, I have worked on all these particular arena. I mean, I've worked on all these particular methodologies towards improvement. And for me, each one of it is a case study because on each type of methodology, my scholars have given or published 2-3 papers over here. But let's take up the very fundamental one as the histogram based approach, that how this, if we pick up this approach, lot of research has been done on improvement of histogram based approach from point of view of your normal digital images and also from point of view of the medical images. So we'll try and work out in this arena that if we pick up this area for working, how we are supposed to start about, then how we are supposed to work out on the domains which are less explored, or how we have to target the regions, which needs further attention to work on it as a research problem. So we pick up histogram based equalization approach for enhancement. And if we apply it to medical image, just take a quick review of this because it's a very common technique. Say we have an input image and we have an output image. We see that this input image, this is a X-ray image, is very blackened over here. If we apply histogram equalization, we see that it has become brightened. So what is happening at the back end is that we are just trying to improve this dark region, which was kind of a washed out in that image, and we are trying to make it bright. How we are trying to achieve this as, at the background, say for this image, we have plotted its image histogram. Histogram is simply the graphical view of this image in the form of distribution of pixels, that these are the pixels which are available and how many pixels are there at a particular value. We plot this in the form of an image histogram. So if we see this image histogram is being concentrated to a location, pixels are bound to a particular region, therefore the contrast is not very good. But if we have spread the histogram of this image, say in a uniform fashion, right, the brightness has been increased. So we are aware that once you are adjusting the histogram to separate the gray levels of an image in a uniform fashion, we see that it is histogram equalization. Now, how histogram equalization operates in its approach. Again, the two input and the output images. We have a transformation function over here, which is known as the standard transformation function for your histogram equalization. Now, we apply the input image pixels to this transformation function, and we get the output pixels in the form that the histogram is now spread out. So this is the transformation function which is helping us to retrieve the content which was apparently lost, because you see this region was very, very dark, but now it has been brightened to a good extent. So how we are achieving this histogram equalization? There is a mathematical transformation function by the name of sigmoid function, or the logistic function. We all must be aware of it. It has been applied globally to all the pixels. So this function is of the form 1 upon 1 plus e to the power minus x. And this is how it looks like. So once we say that we apply this kind of a function to our image, it is going to spread the histogram of that particular image, and it will, increase the contrast, or you can say the brightness part of that image. Now, the mathematical requirement for this kind of a transformation function is that this function should be single valued function and a monotonically increasing function. These are the two mathematical requirements which should be bare by any function which we are being using, say, for or applying for histogram kind of a equalization. So when we say the function has to be single value, somehow it is being practically linked to the fact that if we want to create the inverse transformation, there is a possibility for that existing. That is, the process could be somehow be reversible in nature. Now, if we talk about monotonically increasingness of the function, when there is monotonically increasingness of the function, then in the output image, we see a very good gradation of the images from darkened part to the brightened part. And also, if there are some inversion artifacts, they are also eliminated. So this is the mathematical function for histogram equalization. Now again, what is the constraint of it is, now since this function tries to operate globally on the image, it is creating over enhancement, and with that, you are increasing the contrast of the image, but at the expense of over brightness in the image. So if we see that this is the medical image, if we have applied histogram equalization, there is unnecessary brightness in this image, which may not be required. So an example of an ordinary image, you see the extra brightening in this image termed as saturation region, or we call it the enhanced noise. Now, another improvement to histogram equalization is adaptive histogram equalization, where you are now stretching the grayscale in an adaptive manner. Certainly you have some parameters which we are being adjusted now just to control the degree of the enhancement. But again, if we apply adaptive histogram equalization, you can see that if this is your preprocessed input image, histogram equalization is giving you a not satisfactory image. Although adaptive histogram equalization is improving it to a certain extent, but again, you see the over brightness is still there. That means the noise enhancement part is still not eliminated over here. So the same part is visible in these images also, that even if you see this part, adaptive histogram equalization, the visualization is there, but again, there is over enhancement or noise enhancement. So what is required over here is that adaptive histogram equalization needs further improvement. Specifically, if we are going to apply it for mammogram enhancement problem. So this could be from here, we work on that if we suppose select this as a research problem, how we should proceed further on this. So we want improvement in adaptive histogram equalization, and we want to make it accustomed for mammogram image enhancement. So this could be only made possible when the conventional AHE, that is the adaptive histogram equalization, is modified or improved by a suitable nonlinear transformation function. I mean, any transformation function which somehow overcomes the drawbacks of an ordinary sigmoid function which you are having. So see how we start in this. Now we have learned that this is the plot of the function for histogram equalization. This is your sigmoid function. This is continuous function, and this is a monotonically increasing function. So we say that this is equivalent to a sigmoid function. Now we have already discussed that why it is to be monotonically increasing, it should be real valued, differentiable function. These are all the mathematical properties of this kind of a function. Now, what we have to work on is we want to change this kind of a function so that somehow that function can work on the adaptiveness based on the heterogeneous nature of the breast images. So now let's see how we have worked on this based on the basic properties of this function, like say real valued, single valued, monotonically increasing, continuous in nature. We have, the research scholar has explored a variety of functions which are, very similar to this sigmoid function and giving a similar type of behavior. Like you have a hyperbolic functions, you have simple x upon under root 1 plus x square kind of a function. You have Gompertz function. So these are different functions, mathematical functions, which are giving you similar type of working. Now, what we want over here when we are enhancing these medical images, we are seeing commonly that when you are applying contrast enhancement, the problem is that it is somehow leading to over enhancement. Over enhancement could be good for an ordinary image, but when you are applying to the tumorous part, it is making it over brighten. So somehow you have to stop the enhancement beyond a particular point. So that saturation part has to be stopped. Secondly, that there may be some regions which are already bright in the background and they may not require further enhancement, or if that point is in the background, it may be also suppressed, because if the background is suppressed, then the foreground can be very well enhanced. So somehow, if you think in this manner, that some thresholding, if inserted in this kind of a function, we may somehow achieve upon our desired interest. So see, this is what has been done. This was our ordinary sigmoid function. We have just made its center part little layered somehow to create a threshold. And now you see that below this threshold layer, there is another sigmoid function which is available. And above this threshold layer, there is another sigmoid layer which is present. So now think from this angle that how this can be attained. So somehow this appears to be a linear combination of two sigmoid functions. So the initial condition still remains the same, that that particular function has to be a continuous function and it has to be a monotonically increasing function. So it has been ascertained that you can improve this sigmoid function. You also call it a logistic function. But when you are ascertaining that it should be continuous and monotonically increasing in nature. So this kind of a requirement was obtained by concatenating, you can see, the two sigmoid regions by a linear combination. So now, what has been the significance of this middle layer, that is the threshold part, that there is a sigmoid which is there at the bottom. There is a sigmoid there at the top. Now, both the sigmoids are going to operate, but somewhat in the complementary manner. Because if the sigmoid is below the threshold, it requires, say, suppression. If the sigmoid is above the threshold, it may require enhancement. So this kind of a double working is now being inserted over here with the assumption so that the over enhancement could be worked out, and the places where enhancement is not required, it can be subdued, and also to the extent region in the background where we want to suppress the enhancement, that also can be achieved. So graphically we see it is just like two identical sigmoid functions which are bonded together at the center. So through mathematical analysis, we have come up to this kind of a function which is equivalent to this particular plot. So this is just a linear combination of logistic functions. So you can see that there is one part over here and there is one part over here, right? So this part is somewhere working as your suppressor and this part is somewhere working as your enhancer. And these two sigmoids are connected by a linear combination algebraically. But above that, let's not forget that this is an adaptive approach also. So when we are multiplying it by a gain factor, it cannot be a constant gain factor, because again, if the gain factor is constant and with that same value you are multiply the entire pixel, again it may cause the saturation problem or over brightening process. So care has to be taken that this gain factor should be also not constant, but it should be adaptive in nature. So by mathematical analysis, it has been worked out that this factor is also adaptive in nature. And there are two important control factors over here which are introduced. One is K. K controls the rate of enhancement over here. And another is B, which controls the threshold. Threshold, as I have already discussed over here. And both these K and B exercise dependency upon A. So as we change K and B, the adaptive gain factor will also change over here. So practically, if we test, we come across that K values could be any natural number above 1. And depending upon the image, it can go up to 10, 15 or 20, somewhat more higher. And if we talk about B, it is just a threshold. So it lies between 0 and 1. So we see that how we have tried to overcome the existing regular logistic function with this double or a linear combination of the sigmoid functions. So this is just the methodology we have introduced over here. Now we'll also see how it has been tested. So for that, we'll do simulations. And to start simulation in this domain, very first, what is important is to have a proper repository of the mammograms. So this can be done through different kinds of well-known databases which are existing. They are the Mammographic Image Analysis Society database. This is a repository of mammograms which is being collected through different hospitals under the University of Essex, UK. Then another one is digital database for screening mammography. This is DDSM database. Then you have Bayesian decision support medical image screening database. And all these databases are freely available ones, which has been contributed for further research and benchmarking. What is important from the end of benchmarking is that if you refer to the similar database, you get similar type of images, which are being used by other researchers. So that becomes very easy for you to compare your results with those ones which are already published. So this can be, these databases are freely available from this particular link. And in the set of experiments that I'll be showing you, the results which I'll be showing you, I have used the Mammographic Image Analysis Society database, which is a very common one with 322 digital mammograms being available over there with different types of anomalies. Some pre-processing has been done over here in the form of image normalization. The region of interest is cropped over here, and resizing of mammograms is also done over here. So now, once we have a database for testing, what is important is we should also have a tool for image quality assessment. So image quality assessment over here, we are doing it with two parameters over here. One is contrast difference and another is peak signal to noise ratio. Contrast difference is just calculating the difference in contrast of the two images with the help of the C function, which is Fmax minus Fmin. So Fmax minus Fmin is what it is doing. It is subtracting the maximum and the minimum pixel intensity of that particular image. Now, after contrast difference, we are also calculating peak signal to noise ratio. Although as a general understanding, if we want to see the effect of contrast enhancement, contrast difference could have been sufficient. But we are also calculating peak signal to noise ratio just to calculate what is the final level of signal to noise ratio in the image. That means you want to ascertain that this particular image is not enhancing the noise. So we are calculating peak signal to noise ratio also. So these two parameters we'll calculate for these different set of mammograms over here. And what we see over here, that we have compared the two approaches. One is the adaptive histogram equalization and one is the improved one which we have used. And you can see there is a major difference between the contrast difference values. Say this is 0.2, 0.8, 0.17, 0.9. And then peak signal to noise ratio also is enhanced. That is, say this is 54 and this is 66. So increment in PSNR means that the enhancement is not accompanying any noise amplification. So that means the noise amplification is also controlled over here. Now see, when we have applied this on our mammograms, what is the effect on those images? So you see that this is the input image and this is the output image. This is the input image and this is the output image. But I don't think that this image looks to the kind of expectation that I showed you in one of my previous slides, because you know this, if you compare this image and this image, what you see is that there is only slight improvement in the contrast, and which is, you know, somehow very much equivalent to that of your conventional image enhancement algorithm. So that means something is going wrong over here. But the dilemma is that contrast difference is increasing. Your peak signal to noise ratio is also increasing. So you are in a kind of a dilemma situation. So there is something which is missing. And what could be that missing part? The missing part is maybe we have not tuned the parameters properly. That means we have two parameters with us, that is rate of enhancement and the threshold control parameter B. But certainly they are not tuned. So we go on for a practical tuning of these parameters. And when we tune the value of K, we see that, say for a particular range of values, we are getting the peak. When you tune the value of B, we again see for a particular range of values, you're getting the peak. So that means certainly K and B should be selected in a particular range, then only we can apply it to a particular algorithm. So what we have done, we have run this analysis on different types of images, as we had three categories of images with us: fatty, glandular, dense. And we see for every set of images, the K value and the threshold value both the values are coming slightly different. The reason being, could be possible that if you have a fatty image with you, maybe the rate of enhancement that you require is this much, but maybe if you have a dense image with you, you need more enhancement. So you have that increment in the value of the enhancement factor. But again, that enhancement should not subdue the effect of noise. So over here, there is again change in the value of the threshold. So these are the optimal set of parameters which are being then derived after running it on different sets of images. We have converged to these set of parameters that if this category of images being applied to this set of parameters, we are supposed to get better results over here. Now, suppose we have a original mammogram. This is the region of interest. We say that this is a circumscribed mass over here. So this is histogram equalization. When you are applying adaptive histogram equalization, it is this. So again, here noise is enhanced. Here noise effect is reduced, but you see the image is not promising in terms of sharpening. But if we have applied our improved AHE with this new nonlinear function, this is the kind of image we have got. And certainly we see the background is suppressed, the foreground is enhanced, and there is also reasonable amount of sharpening in this image. Let's see another example. We have, say, this image. Over here, you have again a tumor over here. This is, say, a speculated mass. As we can see the radiating lines over here, this is a malignant tumor. When we apply histogram equalization, you see this kind of an image, which is very, very much, you can see over enhanced over here. AHE, normal AHE has controlled it to a greater extent, but the overall visual quality of the image is still not good. But when we have applied this new function over here with adaptive histogram equalization, this is the proposed output which we are getting, which is fairly better than these two. Another important thing is that we can also locate over here that if this is the tumor region, there are few calcium dots are also quite prominent over there. Now, there is a diagnostic prominence that these calcium dots may go out on their own, or later on, they may get converted to further tumors by clustering. Another very good example is this image where we have input microcalcifications. We see when histogram equalization is applied, over brightness is there, noise is introduced. If we try to control it with the AHE, somehow the result is again unpleasant. But if we have applied this proposed function, you can see that these calcium dots are now very, very sharply visible, right? To the extent that if you zoom it, you can have a count of these dots as these dots, that how many dots are existing over there. So certainly we see with these results that this particular function has rendered above satisfactory results as far as the mammograms are concerned. Now, again, let's do the same part of, that is your image quality assessment. So we have again applied PSNR over here. We have again applied contrast difference over there. But now there is a problem again. The problem is, you see, there is a sharp fall in the value of the PSNR. Now, the image is very, very satisfactory to us from the view because we see that the contrast is enhanced. We see that the image has sharpened also. But somewhere the peak signal to noise ratio value has reduced. Now, if we talk about contrast difference with respect to the original image, there is only slight change in the values, but it is not giving you the giant change in the values. Now, again, a dilemma is there that visually the image is very promising now, but these quality parameters are not giving you a satisfactory answer. So again, there is a need to reiterate the concept of IQ over here, because certainly you are not applying the desirable image quality assessment technique, because say contrast difference and peak signal to noise ratio could be good IQA techniques when you apply to digital images, normal digital images, but they may not be very good when you are applying it to your mammograms. So why this problem is coming, let us understand. The problem is there because, again, some way I would like to recall the last limitation of the medical image, that we know that we are trying to assess the quality with respect to the image, which is not the input image, which is not itself a very clear version of the image. So you're calculating peak signal to noise ratio by choosing that input image as your reference image. So if that poor image is selected as a reference, no doubt your signal to noise ratio can never come up to the mark. Another problem, when we have calculated CD, that is contrast difference, the formula used was Fmax minus Fmin upon Fmax plus Fmin. This was very well known formula that was known as the Michelson's contrast formula. Now, Michelson's contrast formula was superseded later on, say after 5-6 years, by another formula that is known as Morrow's formula of contrast. And this formula says C is equal to F minus B upon F plus B. So you see the structure of the formula is same, but a minor change is made. So what is F and what is B? So rather than picking up the peak values of the there, now we have picked up the average values of the region, but F means average values of the foreground and B means the average values of the background. So you are doing this for your original image, you are doing it for your enhanced image. So you are calculating another parameter by the name contrast improvement index, which is a more desirable parameter when your medical images are concerned. So when we have changed this particular parameter, now this concept which we have applied is not the concept of, you can see the ordinary contrast, but the concept is now of the simultaneous contrast which we have applied, because you see that the small rectangle at the center is now the same, but already we have changed the background, and when the background is suppressed, this foreground appears the best. So that is what happening in the case of the mammograms. So it is not just the intensity of the foreground enhancement techniques, but if you are suppressing the background well, your tumor region will be embossed and sharpened to a very good extent. So when we apply this to the mammograms now, again, we see a fairly good values are being obtained with the proposed method. And now you can see that histogram equalization and adaptive histogram equalization are even giving you negative values at certain places, certainly pointing out that there is enhancement of noise over there. And very high values range is given by your CII, that is your contrast improvement index. And you can see that the values in the range of say 10, 20, at this high 24 values are also obtained over here. So higher the value of contrast improvement index, better is the enhancement. So that is what has been attained over here. You can see this is the enhancements which are being obtained with the ordinary image processing approaches. And once we have modified this with a new transformation function, right, there is a giant change in the working of AHU. So once your enhancement is done properly, it becomes very easily to segment the results. You certainly don't need to apply a very particular segmentation algorithm, a slight thresholding of the algorithm of your enhanced. I mean, if you just can concatenate the result of your enhancement with a good thresholding algorithm, you can very easily achieve the segmentation of your result. So what we inferred over here, that you have got good gray level modification, although you have treated the image globally over here, but your CD, that is the contrast difference value, was somehow better than your original one. You have controlled over and under enhancement by control of these parameters K and B. You have done optimal selection of those parameters. And what we have seen applicatively over here is that the results are good for masses also, and the results are good for calcifications also, although there are not very good results for your denser mammograms. So as a part of continued study, I would like to close my content with this. And as a part of continued study, if anyone wants to work further in this domain, this is the research paper you are supposed to refer as a next study as to what I have discussed in my today's lecture, right? I'm also dealing with this particular journal, that is Recent Patents on Engineering. So it's a Scopus Intex journal. I'm section editor over here. So it's open for submission. Potential persons can submit papers over here. This is another journal which I am working on. And this is a recent conference, Springer conference, which is taking place in Hyderabad, but again, a virtual conference. So prospective persons can submit papers also over here. So I close my lecture with this, and questions may be taken.
Thank you, sir. We have received some questions from the audience. Okay. First question is that what are the major significant causes of breast cancer?
See, significant causes of breast cancer are obviously the biological reasons. They are the hormonal changes. They are the factors. So from an engineering point of view, that is never our aim to study those factors. But what we are interested is where we started my lecture, that we should be, fairly eminent with how the tumor behaviors are changing over there, right? And how we are going to address this with the image processing and soft computing approaches.
Okay, so next question is that can noise removal be done before enhancement?
See, definitely this could be possible in the medical images where the noise is in the form of a visible noise. Like if you take example, say if the noise is somewhere is, Gaussian kind of a noise in nature. Like if you talk about MRI images, the similar model of noise is applicable over there. Like a Rickian model or Gaussian model is applicable. So there you can have a proper pre-filtering and then you can have enhancement. But if you talk about mammograms, mammograms have the kind of noise which is very different from this. And that particular noise is known as the quantum noise. So that noise is coming when your X-ray photons are falling on a region and maybe they are missed from that target. So the impact of this kind of a noise is not that of a visual noise, but what we see in the form of poor contrast. So over here, what you see as a poor contrast is actually the noise only. So that is why we say that when you are improving the contrast, noise is not enhanced.
Okay, sir. Next question is what parameters will A depend on? It was in one slide, in one of your slides.
Okay, A was adaptive gain factor. So the dependency of A, what we have taken upon is on the two factors, because see, we are changing the enhancement factor K over here and we are changing the threshold B over there. So we have tried to establish relationship between K and B and just to change the value of the adaptive factor A.
And the next question is, sir, what causes the calcifications? How do they start to cluster up?
See, as I told, that they are the tiny specks of calcium deposits. So there are milk glands in the breast cancer. Certainly they are the cause for, those calcium deposits in that region. So they start, somewhere they start, they scatter, they cluster and they disappear. But certainly if there is some amount of inactivity over there, they get converted into, tumors. Again, if that tumor is circumscribed in nature, they are benign. So they could be, hailing like that for years and they are unnoticed without any problem. Problem starts when, there is some amount of activity which starts, that is the tumor border starts to distort and the metastasis starts to the other part, other cells or other tissues.
Okay, sir. One more question. Can you suggest which frequency domain technique is best suited for enhancement of mammographic images?
See, we have worked on wavelets also. We have worked on contourlets also as that approach. Both have their own, specifications. As you are aware that wavelet techniques are mostly for your point singularities. So if you are detecting calcifications, wavelet techniques could be good. Contourlets are very good, when you are trying to figure out the contour of something. So try and relate. If you want to get relate masses, if you want to detect masses, some way the controller transform based approaches are much better. So again, that depends upon the kind of case you are working. You need to experiment out and then apply that particular multi-resolution approach.
Yes, sir. One more question is here.
Yes.
After applying contrast enhancement technique, how do we come to know the extent of noise that has been added, and
See,
which denoising technique should be used to overcome it?
See, again, you don't have to apply any specific denoising technique over here, because when you say a denoising technique, it means you applying a filter like something like of median filter or any kind of filter over there. But again, if you apply such type of a filter, that's a very strong filter. It may be very good for ordinary images, but if you apply on mammograms, it may eliminate or, you know, it will erase those details, fine details, which could be, you know, of other diagnostic importance to you. So over here, when you say noise, noise is only nothing but what you see in the form of over enhancement of the tumor region, we technically term as overshoots in the foreground region. So those overshoots, that oversaturation of the pixel is actually termed as noise over here.
Okay, sir. One more question. Breast cancer can be cured in small duration?
See, I mean, we as engineers cannot work on cures. Like, we only can make the predictors in that manner. So most, I mean, if you take the problem of working on the denser mammograms, that means if you have mammograms of the younger age ladies, and then you apply your techniques, and somehow if they are giving you results on a prior age time, you know, at that time treatment is very easy. But generally, when these particular tumors or cancers get submerged at a particular time, at the particular span of time, at that particular age, it is itself a fully grown cancer that at that time the treatment becomes difficult. Now, there is another irony over here. Let me tell you. There are population screening programs also, which are being done for the ages less than 40, but they are all, how recommended they are, you should understand that there is only a doubt that I mean, you may just some candidate may just have a lump in the breast region. It could be just a simple lump. It may not be cancerous. But if you just go for, you know, repetitive mammographic screenings just for your clarification of doubt, now the problem could be that even that lowest dose of that X-ray can trigger that benign tumor and it can convert it to cancer. So again, frequent screenings also create problem when you are doing early diagnosis. So it's, you know, again, a domain full of challenge. That is why a most preferred domain of research, not only for the medical experts, but for us as engineers also.
Okay, sir. One last question I have received now. Male breast cancer possible or not? If possible, at what age?
Yes, it is there. It is possible. And that is, you know, I mean, very, very niche area of work, which one of my scholar has taken up. Age groups are not very clear because itself you have very little papers which are yet available on that. But most probably in a year or something, we'll be producing some published work in that domain also. So probably then I would be able to comment on that in a much preferable instances, you can say.
Okay, sir. One more question I have received now. Can thermographic cameras not be used for imaging? That would not be invasive like mammography?
Yes, that could be also there. You also have a similar diagnostic images in the form of the best thermograms, but again, they are not the more preferred domain is comparison to the initial screening is concerned. Your mammography and your ultrasonography are the initial predictors, and those are the stages which could be used at the advanced stages where you want to detect something.
Okay, sir, one more question is here. Conclude the exact technique used in each section like image data, source pre-processing, enhancement, segmentation, feature extraction, and neural networks.
See, over here, nothing much has been done in the form of the pre-processing, because once you are referring to a database, if that database is a good one, initial pre-filterings are already done over there. over here, what we have done is we have only normalized that particular image. Normalization is just you are, trying to rescale your pixels to the range 0 to 1. Just to make the work more focused, we have extracted the region of interest, but that region of interest is also extracted based on the indicators given by the radiologist in those databases. So these are the two pre-processing which have been done over here. Now, suppose you have some database where you have 3-dimensional, or you can say your RGB images are there. You can go for the change of the color domain and then operate on those images. That is just pre-processing over there. So again, pre-processing varies on the kind of database you are picking up.
Okay. If anyone has any more questions, then please can ask. Otherwise, we are winding up this session. Okay, so no more questions. Now I would like to invite Professor Swati Gupta, Head of Department Electronics and Communication Engineering, for a vote of thanks.
Grant sir, it was truly a journey of knowledge with you today. And with so many questions popping up, I believe the participants were listening it very carefully, and they have got many ideas, and many of their queries got solved through your.
See, actually the duration of the talk was less. Otherwise, where we go for 3 days or 5 days kind of a program, and where we are having a daily lecture, we take up each and every case study. So as this was just an initial case study, so maybe the nature of questions would have been more obviously, but the problem was so selected in the manner that somebody should get an idea that how should we go in for change of problem, because we always remember that we as PG scholars or research scholars came across similar issues that we never used to understand how to change the problem and how to do something new in that.
True.
So the major point was to give an impetus that how we should think in that manner to change the basic functionality of a function. That was just the biggest example of it.
I also personally believe that whatever was discussed, I thought that whosoever are doing research in this areas or planning to do research in this, they'll be getting a lot of fields now to carry on, because sometimes it's the most difficult task to actually find out the field in which you want to go for research.
Exactly.
That is the main. I believe that half of the research is done over there only.
Right.
And by your things, more than I believe many options we have got where we can do the research. And I believe, Grant sir, we can have such more number of sessions with you.
Surely. I would be happy to, keeping the research just in the black box is not a, aim. So it's really good to, to share the ideas like this.
Thank you so much, sir, for your time. You are such a busy person working on so many projects and books, and to take out time for talks is a very difficult thing. I know.
My pleasure, ma'am. But just a holiday is just the best option for that, and especially these COVID times are another, opportunity.
Yes. COVID time will definitely come as an opportunity for the admissions, I believe, because we can have as many webinars and sessions to discuss the things. Thank you so much, sir. Thank you so much.
Thank you, ma'am. Thank you very much, sir, for giving us your valuable time. And thank you, everyone. We will start our next session tomorrow sharp at 9:30 a.m. Okay. Thank you, sir.
Okay.
Thank you, sir. Thank you.
My pleasure.
Thank you, sir.
कल ना 9:30 बजे शुरू करना पड़ेगा।